Okay? So vertical circles. I don't know if I have time to fit the whole story in and do the lesson, and I got to get to the lesson. That's more important. A person rides on a Ferris wheel. How many of you have been on a Ferris wheel before? Okay. Key idea in a Ferris wheel is it's a vertical loop and your head always points upwards. Doesn't mean your head always points towards the middle. When it's at the bottom, your head's pointing towards the middle. When you're on the top, your head's pointing away from the middle. Unlike a roller coaster loop, where your head is always pointing towards the middle, because when you're at the top of the roller coaster loop, your head is pointing down. Those are going to be the two main types of vertical loops. Okay? So a person rides on a Ferris wheel. They sit on a Newton scale that measures normal force. Of course, a scale measures normal force. I've tried to beat that into you guys this year. At the bottom of the Ferris wheel, what does the scale read? And convince me. Does the scale read A, mg? B, does the scale read a bigger normal force than mg? Or C, does the scale read a smaller normal force than mg? You know what this is a good job for? A free body diagram. Or you know what? Let's label the forces right on our Ferris wheel. See the person sitting there? What are the forces acting on this person? Get the obvious one. Gravity. Right? What else? Is this person sinking into the ground? Is this person falling? Nope. So what else? What's pushing them up? Okay, the normal force through their seat is pushing them out. Ah. And Peter, what path is this person tracing out? So where must my net winner force be? Pointing towards the... And the only way that can occur is if I draw the normal force bigger than gravity, smaller than gravity, or the same length as gravity. The answer has to be B. In fact, as an equation, it would be this. Winner minus loser equals MA. Oh, wait. You said we're moving in a circle? MAC. This is sort of the version of the old elevator question from Physics 11, but now we're moving in a circle. It says, explain your answer using principles of physics. Right there. Good free body diagram would do it. Because we've said if you're moving in a circle, you must be accelerating towards the center. And the only way you can be accelerating towards the center is if your net force is pointing towards the center, which means normal force has to be bigger. That's why at the bottom of a Ferris wheel, although Ferris wheels don't go very fast, you do feel heavier. Certainly at the bottom of a roller coaster loop, you feel like you're being pushed into your seat. You're not. It's the normal force having to push back up against you harder. So on a Ferris wheel, people feel light at the top and heavy at the bottom. Why does this happen? I think we've already convinced you that you feel heavy at the bottom. Let's convince you that they feel light at the top. Let's do a free body diagram for the very, very top. What are the forces acting? Get the obvious one. What else? Normal force. What path is this person tracing out? Where must the net force be pointing? So the biggest force has to be pointing. So I better draw my normal force smaller than mg. You'll feel lighter at the top. If you're going really fast, you'll feel way lighter. In fact, if you're in a car going quite fast and you go over a hill, you can actually reach the point where your normal force vanishes and you feel weightless. That's when you feel like you're about to leave the ground. Okay? And again, I'm not saying gravity has vanished, William. What I've been trying to convince you both last year and this year is what you guys think of as gravity, what you guys think of as your weight, it's the normal force. And if you remove that, you'll be, I feel like I'm floating. Right? Oh, and in fact, if a car wants to, say, go over a curved hill, and if it actually leaves the ground, like, for example, in the movie chases that take place in San Francisco or something like that, what would that look like? I'll let you think about it. So why does this happen? I left a paragraph to write stuff, but I think that picture is worth 1,000 words, yeah? If you really want to, you can say centripetal force, which is the net force, must point towards the center. But I think you got it from the free body diagram, but I know some of you like to write stuff. In the previous example, The Ferris wheel is a rigid wheel. The top and bottom of the wheel will always have the same speed, which means the circular motion is uniform. This is not always true. Consider a pendulum. Watch close my little vertical pendulum here and ask, is the speed constant? I think at the top, what's happening to the speed? Slowing down. At the bottom, it's speeding up. In fact, I can probably find an equilibrium point. I can probably get it really, yeah, I'm almost getting it so it starts to fall. You can hear the click as it comes back together a little bit. It's tough. You guys can't see, but I can certainly feel it through my hand. So it says here, write force equations for the vertical pendulum at the top of the loop and at the bottom of the loop. Okay. At the top, what are the forces acting on the pendulum at the top? Get the obvious one. What else? No normal force. What else? Tension. I have two forces acting inwards. At the top, my equation is gravity plus tension equals MAC. What about at the bottom? What are the forces acting on this pendulum? Get the obvious one. Gravity. What else? Tension. Who has to be winning? Why? Because we're moving in a circle, and my net force, my winner, has to be pointing towards the center. And hopefully also now you're seeing, Claire, why I went on such a rant last day saying FC does not appear on your free body diagram, because in this case, FC is actually the vector sum of those. It doesn't show up. It's tension minus mg equals MAC. So in a vertical circle, there can be tangent forces that speed up the object. Gravity in this case. So when it gets dead sideways, gravity starts to accelerate it down. As soon as it starts going back up, gravity starts to slow it down. So we have a force that's acting tangent to the radius when it's not at the very top and not at the very bottom. You still have a net inwards force of ma, which is mv squared over r, or m for pi squared r over t squared. And in a vertical circle, at least at this stage, Alex, there will be either no horizontal forces, almost all the time, or there might be two that add to zero that you can ignore. Like on a Ferris wheel, there's probably the force from the axle pushing left and pushing right to hold it in place. Whatever. We're not going to write them. Okay? But this gives us some interesting stuff. Turn the page. I like this question. I like this question. I like this question. A 70-kilogram passenger is moving at 10 meters per second at the top of an upside-down roller coaster. Find the force that the seat exerts on the person. Okay? This is a bit different from the Ferris wheel. Don't just start memorizing stuff. We have to think each time. We have to go back to first principles. And for forces, our first principles is a free body diagram. Or heck, let's label the forces on this picture. What are the forces acting on this person? Get the obvious one. Gravity pointing which way? What else? You said it. You're right. Normal force pointing which way? Down, because they're upside down relative to us. The normal force is also pointing that way. And in fact, that's good because this question said, find the force the seat exerts on the person. What force are they really talking about when they ask that? Normal force. Who's winning? This time it's two of them are winners. Not a tie, because I don't think they're the same size, but two winners, no loser. I think my equation's going to look like this. Is that okay, Jordan? Yep. What are we being asked to find here? Normal, get the Fn by itself. Just minus mg, that's not too bad. MAC minus mg. Now the only question is, which A do I want to plug in? The one with the T or the one with the V? By the way, in this question, I gave you the V, and I'm going to use that. If you're actually analyzing amusement park rides, the easiest thing to get is the period, because while you're standing in line, you got a stopwatch, you got your phone, you just time how long it takes for a person to start at the top and get back to the top. You can get that while you're standing in line, piece of cake. But in this case, I gave you the tangent speed. So this is going to be do the masses cancel this time? No. Now, this isn't saying that the ride behaves differently. This is saying that if you're a heavier person, you'll feel heavier relative to a lighter person who feels lighter. Proportionally, it'll be the same, but if suppose the answer was, it's not, but suppose the answer was you feel twice as heavy, well then a 50-kilogram person would feel they were 100 kilograms, a 30-kilogram person would feel they were 60 kilograms, so the mass shouldn't cancel. It's going to be a different answer no matter what. Here we got 70 10 squared over, R is in the picture, minus 70 times 9.8. What do you get? $70 times 10 squared over 8 minus 70 times 9.8. Oh, you get 189 newtons even? Yeah. Nice. Compare that with their normal force. So normally they feel like they have a weight of 686 newtons. Hey, will this person feel lighter or heavier at the top of the loop? Heavier. They're going to feel like they're about to fall out. They would reflexively probably grab at their shoulder straps because they would feel like, even though they still actually have a fair safety margin because the chair is still having to push against them to push them in a circle, they would feel such a light normal, you'd scream and it'd be a good ride. Follow-up question I asked in example 5. In the previous example, what would happen to the normal force, the scale reading, what the seat says, if the coaster moved slower or faster? And convince me. Well, I think what we're talking about here is that, in fact, you know what? If I was answering this, first thing I would do is I would write down, well, hey, the normal force equals and if I hadn't done that, William, on the previous question, I would quickly derive it with the I would show them this stuff as well if I hadn't already done that. Is that okay so far, kiddo? Okay. So here's the question. As v gets bigger, as you speed up, what happens to the answer to that equation? What happens to the normal force that you get? Bigger, smaller, or stays the same? That's why if you go through a loop really, really fast, you feel like you're really being pushed against the cart. You feel like you're heavier because the actual seat itself is having to push harder against you. California Screaming, Elijah and Hakeem, the loop, the classic loop. You're going through there pretty fast. You actually feel heavier than just standing. Okay? They've got the V big enough that you end up with an answer bigger than plain old mg. That's doable. Oh, and as V decreases, the normal force would decrease. Feel lighter. What would happen if you went at just the right speed so that the answer to this equation was 0, so that the normal force exactly equaled gravity? If you weren't wearing a seatbelt, you'd probably be in trouble. What would happen if you went at a speed so that this number, mv squared over r, was smaller than gravity? The roller coaster would fall off the track unless the wheels were somehow secured. It would get almost all the way up the loop and then come crashing down. Okay, that's all in that equation there. So we don't want that to happen, and they build a good safety margin. In fact, later on today, or no, I think a couple lessons from now, we'll calculate how fast you have to hit a loop in order to get through it safely, in which case, how high does the first hill have to be so that you'll make it through the loop. It's a fairly easy calculation. Okay. Example 6a says, if the pendulum in example 3 or the upside down coaster of example 5 were moving at minimum safe speed, what would that imply about the forces? And find an expression for the minimum speed. You know what? I think I'm going to find an expression for the minimum speed first, because I think that's going to help me answer part A. So we just did the right hand, the upside down roller coaster. We said normal force plus gravity equals mv squared over r. We said this. What would the normal force be if you were going at the minimum safe speed? Okay. At minimum speed, so you'd have this. In fact, Curtis, I would argue, I can give you the expression for the minimum safe speed. I think the minimum safe speed is the square root of GR, is it not? I think times by r and square root. That there, 9.8 times the radius of your roller coaster. Take the square root of that. If you're going slower than that, you're not going to make it around the loop. You're either going to come crashing down, or if the wheels are like locked in place, it would go and slide back down. Oh, what about the first one? If I go at the minimum speed, watch close and tell me if you notice something. I'm going to go minimum speed, watch. Oh, that's too fast. You see it? Look at the rope, look at the string. When I go minimum speed, what do you see? Okay, you know, there was below minimum. I think if I go exactly minimum speed though, what can you tell me? How big is tension? I think 0. I think minimum speed, just like normal force is 0, I think when you're talking about the pendulum minimum speed, tension is exactly 0. No more, no less. Who are we looking for out there? Oh, okay. I thought I saw people looking over my shoulder outside or something like that. So I think here we can say at min speed tension equals 0. Oh, you know what? We're going to get exactly the same equation. Tension's going to cancel. We're going to have mg equals mv squared over r. And you know what? We're going to have, again, that's kind of convenient. And I guess it doesn't surprise me now that I think about it. I can say, okay, yeah. All I want, if my net force, if my centripetal force exactly equals mg, that's my equilibrium point, because there's no other unbalanced or extra forces kicking around. Example 7. If we spin a bucket of water fast enough, it is possible to momentarily invert the bucket and yet not have any water fall out. Oh, I sense some doubt. Okay. Why does the water not fall out? I'll give you a couple of options. Oh, that wasn't supposed to be there. Had the answer sitting there for a second. Got to line these up properly sometimes. Hey, Marshall fills half a bucket of water. He swings it in a vertical circle. If he swings the bucket fast enough, the water won't fall out because of the bucket at the top. This is because the A, inward acceleration of the whirling bucket is at least g. B, the fall of the water in the bucket matches the motion of the bucket. C, the bucket is made to fall at least as fast as the water would fall if spilled at the top from rest. D, all of these. Or E, none of these holds water. Sadly, if you were quick, you already glanced at the answer. What did you see the answer was? Or did you see the answer? Maybe you didn't. You saw the answer. It said D, yes. I got to line these up next time. So, believe it or not, this also demonstrates how the ISS orbits Earth. The ISS is falling, just like the water in the bucket is falling. But what we also give it is just the right sideways velocity so that it's falling exactly matching the curvature of the Earth. We'll talk about orbits in a couple of days, but we're going to start to already think about outer space and orbits. We can see this by going back to our notes and doing a good free body diagram, because this is a job for a free body diagram. What are the forces acting on the water? Get the obvious one. What else? Normal force. I drew them the same size. I don't know how big they are, but I just wanted to make sure I could see it. We would say this: when you're moving in a circle, right? Oh, and as long as the normal force is bigger than or equal to 0. How could you have a negative normal force, Mr. Dueck? Well, really what we're saying is the maximum case is no normal force. You have this. Oh, boom, boom. Oh. Same expression as we had earlier. As long as V is bigger than or equal to the square root of GR, we stay dry. We stay dry. Because there's still a net force that's pushing the water down and pushing the bucket down, and since they're both accelerating at the same rate, the water is going to stay inside the bucket. Kind of similar to the dropping the water bottle with the leak from the deck that we did up, from the little porch that we did up there. And we noticed that the water stopped leaking while the bottle was in free fall. Put your pencils down. So let's look back again at space stations. We treated space stations as horizontal circles, but you know what? You can think of them as vertical circles. It really depends on whether you're looking at it from the frame of reference of us, the viewers, staring at the side of the space station from straight down, or whether you're imagining you're the person standing on the floor looking up, because then it's a vertical circle. So a space station has an outer radius of 140 meters. The space station rotates so that the occupants at X experience an acceleration of 9.8 meters per second squared. Hakeem, this goes a little bit to the question you were asking earlier today. At what acceleration will the occupants at Y experience at the 100 meter radius? You know what I can tell you? Less than 9.8. They're going to feel lighter. How much less? Well, I'm kind of seeing two parts. Okay. Let's look at those astronauts sitting at location X. What are the forces acting on them? Get the oh, sorry. They're in outer space. Don't get the obvious one. No MG. What else? What have we said in this space station diagram? What's the other force acting on them? Normal force pointing which way, Jordan? Okay. So at the 140 meter point, my equation would look like this. In fact, at the 100 meter point, my equation would look like this. Hakeem, again, this goes back to your question. I think what's the same at these two locations is not the speed. I think here and here, they both have the same period, the same time to go around. So I'll even make a little note here. I think t equals t at 100. Good gosh, having a tough time here. T at 100 meters equals period, or t at 140 meters. So I think I can say this, m4 pi squared r over t squared. Oh, and they've told me that at 140 meters, I feel that. This is going to be m4 pi squared r over t squared. What are they asking me to find in this question, by the way? Which acceleration? See, here's what I think they're asking me to find. G, but G at the fake G at 100 meters. What would gravity be like there? I think that's what it's saying it wants me to find. Yay. Yes? Maybe I have enough. Let's see. Do I know the 4? Yeah. Do I know pi? Yeah. Do I know the radius? 100. Do I know the period? I bet you maybe we can find the period from this information here. Maybe. Let's see. Here, I know G is supposed to be 9.8, the real G. I know R is 140. Yeah, I can find the period. How? I think those will swap places because stuff moves diagonally. Yes, William? I'll move the t squared to the top. I'll move the g to the bottom. And that's going to give me but to get rid of the squared, square root. Put your calculator down, Hakeem. You know what? I think I'm going to leave this as t squared. You know why? Couldn't I actually just plug all those variables right into there? And I'm seeing, I bet you a lot of stuff is actually going to cancel out quite nicely. The only problem is the r's are different. So I'm going to call this R1. I'm going to call this R2. Is that okay, Claire? I was worried I might get those mixed up. See, I'm going to get this. G at 100 meters is going to be 4 pi squared R2 all over 4 pi squared R1 over G. We could have crunched the numbers, Hakeem, and if you feel more comfortable doing that, actually solving for the period and then just carrying it over with your answer button, you can. But since I saw all this stuff canceling, I couldn't resist. Because I think what's going to happen is this. Yeah? And? Yeah? So I think I'm going to get R2 over How do I divide by a fraction? Who remembers their math 8? Because I am dividing by a fraction. So I think the g at 100 meters is going to be the second radius, 100, times g over. I kind of like that. I don't know if that's significant, but it's the second radius times g. That GR has showed up before in other situations over the first radius. It almost looks like it's like a ratio or something like that. It's going to be 9.8. The second radius is 100. First radius was 140. What will the gravitational field strength, the fake gravitational field strength, the artificial gravity feel like at 100 meters? Now I'm going to go to my calculator. I think this might even work out evenly. Holy smokes, yeah. They'll feel an acceleration of 7 meters per second squared. You would notice that if you were living there, you'd feel a little bit lighter, and especially if you'd grown up on the Earth, stuff when you dropped it, when you knocked something off of your desk, it would fall a little strangely to you. It would still fall fairly quick, but something would just bug you as looking wrong. So that one there, Aaron, I could have done under horizontal circles or vertical circles, but it's a neat question. Oh, have I done a few space station artificial gravity questions? Figure out why. It was over some of your heads, wasn't it? Okay. I like this question. I like this question. I like this question. I think this is the last one. Yeah, last one too. Okay. A 95-kilogram person rides a Ferris wheel, which is rotating uniformly, not changing speed, a little nicer. The centripetal force acting on the person is 45 newtons. What force does the seat exert on the rider at the top and at the bottom of the ride? You know what? Since it's a top and the bottom, how about... Fair enough? Now, it's asking me to find the force that the seat exerts. In terms of our physics language, what force is it really asking me to find when it says that? Normal force. Okay, so I'm going to find the normal force. That's going to be my answer. Okay, at the top, what are the forces acting on this person at the top? Get the obvious one. Sorry? Gravity down. What else? Should I draw normal force bigger, smaller, or the same size as gravity at the top? Sorry? Smaller? So my equation at the top is going to be, it's going to be what? Winner, gravity, minus loser equals MA. Actually, you know what? Well, MAC, except in this case, they actually gave me the centripetal force. They said, hey, the answer to MAC is 45. They didn't give me the radius. They didn't give me anything else. That's fine. They're saving me some time. What am I trying to find? The force. Which one? This isn't Star Wars. Okay. Plus that over. Yes, Peter. Minus that over. I met your little brother yesterday, by the way. He was great. So, Peter, gravity minus, I'll even put an FC instead of MAC, equals FN. Did they give me the mass? I hope they did. I've scrolled down. Did they tell me the mass of the rider? Because the masses don't cancel here. 75 minus 45 equals the normal force. Hakeem didn't reach for his calculator, I hope. Hopefully he said, oh, I can go 75 minus 45 in my head, I hope. Hakeem, in your head, what's 70? Oh, wait a minute, Mr. Dueck. What have you done as a mistake here? What have you done wrong? Yeah? Oh, don't forget, don't get carried away, because we get what's happened. The other thing I see kids do is they get so concentrating on getting the circular acceleration, they get sloppy with the other ones. I can't imagine anyone ever getting sloppy on like a first or last question of a test or something like that and making a sloppy mistake ever. So you're saying put a 9.8 there? I guess you do need a calculator, Hakeem. I stand corrected. What is 75 times 9.8 minus what's going to be roughly 750? It's going to be around 700. 600? 690? Even? Compare that with normally they would feel if they were just standing still. 735 newtons. They feel a little lighter at the top. And if you go on a Ferris wheel, if you're really looking for it, unless it's a really slow-moving Ferris wheel, you can feel a little lighter at the top. At the bottom, what are the forces acting at the bottom? Get the obvious one. Which way? What else? Pointing which way? Bigger, smaller, or same size as mg? Ah. So here, my equation is going to be winner minus loser equals, and instead of writing MAC, I'll just put FC since they gave me FC was 45. Here, it's going to be FC plus mg. Conveniently, Hakeem, I seem to recall that mg was 735 and FC is 45. I might, perhaps, maybe be able to do that in my head without a calculator. If I chose to do that, Hakeem, in my head without a calculator, what would I get, my friend? 780 is correct. And again, as you notice, folks, pigs are flying. Okay? Now, I could go in more detail. You're going to see a Ferris wheel question or a roller coaster question. What else could I ask? If I gave you the radius, I could then instead say, hey, what speed does it have to travel at if I gave you the centripetal force? Or I could tell you, ask you, hey, what's the period of rotation? Or in other words, anything that appears in these equations, I can say, get that by itself. What's your homework? Number 1. Number 2. Now 3, the angles, this is just to see if you can figure it out. We're not going to be looking at these situations, but it's nerdily cool. I don't mind showing it to you. 4 is good. 5 is good. Am I going to assign everything? Let's see. Yeah, sir, 6 is good so far. Ferris wheel, yeah, 7 is good. Maybe I am going to assign everything. I don't remember what all is on this. I'm going to assign 8, but I think you're going to find that in number 8, so number 8 says a fighter pilot can withstand a maximum acceleration of 8 Gs. I think you may find that your free body diagram on this is a bit tricky. I seem to recall liking this question in that, hey, it's a fighter pilot, what radius can you go without blacking out? Not so much liking this question because I think 8 Gs is not what you want to plug in. I think you want to plug in either 7 Gs or 9 Gs because I think they're taking into account the fact that you normally have 1 and that the maximum... Anyways, I'll let you think about it. A 9 I like. Please notice both in number 8 and number 9, the speeds are kilometers per hour. You have to do a conversion. So I skipped 10 and 11. 12. You got lots of time.